To get started, I'll go over a brief outline of what we're going to cover in the presentation. So we will talk about why we need to know what the detector efficiency. We'll go over minimum detectable activity, or the MDA, the uncertainty associated with the counting of radioactivity, using the decommissioning tool that DNSR has sent out to licensees already to calculate or to convert CPM to becquerels per centimeter squared to calculate the MDA and the uncertainty. And then finally, I think the reason most of you are here, we're going to go over a few methods for measuring and establishing detection efficiency. And once again, a reminder, there will be a full Q&A session after the presentation. Okay, so just a few basics here. DPS, you've seen, means disintegrations per second. It's also the definition of a becquerel, a unit of activity. And then we have CPS, counts per second in a detector. So they are not the same thing. The ratio of the two is what efficiency is. So the point here is that not all of the emissions, when you're measuring radioactivity, will even reach the detector or will be counted by the detector. So the number of becquerels on the surface will not equal the measured CPS. Even if we have a perfect detector and we're measuring contamination on a surface, you shouldn't get more than about 50% efficiency because roughly half of the emissions will be traveling away from the detector. There are exceptions, but generally speaking. So why do we need to know detection efficiency? So regulatory criteria that are set out in license conditions, for example, are not given in counts or counts per second or counts per minute. They are given in surface activity, so becquerels per centimeter squared. And of course, your detectors are just giving you a count rate, counts per second, counts per minute. So we need to be able to convert, to go from the counts per minute to the becquerels per centimeter squared. And to do that, we need to know the instrument's detection efficiency for a given radionuclide. So what we have up here on the screen is a very common set of regulatory criteria. They're for DNSR. They're common. They're in the license conditions. So we have different radionuclides broken up into three classes, class A, B, and C, based on risk. And we have the levels at 0.3, 3, and 30 becquerels per centimeter squared, averaged over 100 centimeters squared. So this applies to decommissioning license criteria. In that case, it would be fixed plus removable. So you do have to do some direct measurements for that. It would also apply to just work surfaces and public surfaces. In that case, it's removable, so you can swipe or you can do direct as well. Another common criteria that's expressed in becquerels per centimeter squared would be transport criteria, so the exterior of a transport package. It's stipulated in the transportation regulations, so 4 becquerels per centimeter squared for beta gamma emitters and 0.4 becquerels per centimeter squared for alpha emitters, and that would be averaged over 300 centimeters squared. Okay, what are the factors affecting detection efficiency? So we have different factors that can change the detection efficiency. We have the distance to the source. Now, the distance to the source will affect the attenuation that alpha particles and beta particles will see in air because they are affected and attenuated by air, especially alpha particles. The distance to the source will also affect the geometry of the detection window to the source, which is the second bullet. So basically, the further you are, the more of the edge emissions from the surface you're missing. So that also will affect the efficiency. Then we've got things like window thickness or the energy cutoff of that window. So we have to remember here that beta emissions are a continuous spectrum, and we'll cover this more in the presentation. So basically, given a certain window thickness, below a certain beta energy, they just won't get into the detector and won't be able to be counted. And then above a certain cutoff energy for that window thickness, they will get into the detector and be counted. And then we have gamma energy. So the energy of the gamma rays that you're trying to detect will affect the likelihood of interaction with any given detector. So all of these factors will affect detection efficiency. So this slide here is just an overview of just some of the types of detectors that you could see. So we start with definitely the most common and most ubiquitous one, which is the thin window GM. GM is Geiger-Müller. And we refer to this detector as the pancake. I'm sure you've all heard of it and used one. So it's capable of detecting alpha, beta, gamma radiation, but cannot discriminate between them. It just will count all three types of radiation with varying degrees of efficiency. Then you have some larger detectors. For example, we have a thin zinc sulfide detector, which is sensitive to alphas, sandwiched with a plastic scintillator. Sometimes these are called dual phosphor detectors. And they can discriminate, so you can count the alpha counts and the beta gamma counts separately, or you can sum them all together. Especially with these digital meters, you can actually have a dual screen showing you both channels, so that's convenient. Another detector that's used by licensees, the Berthold LB124. There's also other models like the LB122. So this is more of a proprietary thick zinc sulfide scintillator, and it can also do alpha and beta gamma discrimination. Then we've got sodium iodide scintillators. They're also quite common, so thin ones, which would be optimized for both high energy beta emissions or low energy gamma emissions. And then we have thick sodium iodide detectors, which would be optimized for high energy gamma detection. Okay, so how do we establish detection efficiency? So we will examine 4 different methods, and they're in order of regulatory preference, and we'll go over them in turn later on. So we will be looking at the first one, which would be simply buying a NIST traceable planar source, where the calibration nuclide is the same as the target nuclide. So the target nuclide, of course, is the nuclide that you're working with, that you're trying to measure out on a lab bench or in the field or whatever. Then number 2, if you can't get a NIST traceable source or the nuclide is the same as the target nuclide, you would look at getting a NIST traceable planar source where the calibration nuclide or nuclides are suitable surrogates for the target nuclide, and we will go through examples. Next would be making your own source of known activity. So for this, you have to have a way of establishing the activity. We'll go over some examples. This is, and then in this case, of course, the calibration nuclide would be the same as the target nuclide. And then the least favorable method would simply be to look up published efficiencies or suggested efficiency values. So this could either be on a manufacturer's website, or you can ask us, you can ask myself or your licensing specialist for a reasonable and conservative efficiency to use. And note here again, efficiency must be verified and documented at minimum annually. So something to consider. Okay, instrument detection efficiency. So there's the formula. Okay, it's simply the counts per second, the net counts per second that you measure from the source, the calibration source, divided by the total source activity. So the net would be the counts, the raw counts that you measure, and then you would subtract the background counts. And you have to make sure that you do this in counts per second because the becquerel is by definition disintegrations per second. And if you want to express the efficiency in terms of percentage, just multiply by 100 for 100%. So things to remember, if you're counting in counts per minute, a lot of handheld detectors just default to counts per minute. Just remember to convert that to counts per second by dividing by 60. Always use the total activity of the calibration source. Okay, so that yields the absolute 4-pi efficiency. So this is mentioned because sometimes you'll buy a calibration source and you'll see on the certificate, it might say the activity, but it might also say 2-pi emission rate. So that would be the number of emissions that are coming up off of the source in one direction. What we want is the absolute activity, not the 2-pi emission rate, to put in the denominator in the formula. We don't want to shield the sources. Like don't put, if you're making your own source, for example, on a swipe, do not put it in a plastic bag. We don't want to shield any low energy electrons. Unless, of course, we're doing it on purpose because we're trying to isolate counts for specific emission types, which we will get into an example of that. We want to try to use a consistent and repeatable source to detector distance. So, roughly 1 centimeter. Basically, you're trying to mimic, roughly the distance that you would use when you're out on a lab bench or in the field, actually measuring contamination. And for this, we would highly recommend some kind of jig. It doesn't have to be complicated. It can just be like 2 pieces of wood or plastic, just so you always use that same distance year after year to measure and establish the efficiency. So that would be the distance of the detector to the source. Always measure background in an area devoid of nuclear substances. That's pretty obvious. Counting time should be the same for source and background. We will get into specifics on counting time as well. And then when we have nuclides with short-lived progeny in equilibrium, like for example, strontium-90 and yttrium-90, we want to consider the activity of the parent only when we're calculating the efficiency. Okay, the formula for converting counts per minute to activity, and this would be for removable surface activity for a wipe, but it's the same thing for direct. It's just that there's no collection factor. So these formula are published in RegDoc 2.7.1. So it's just the net counts per minute. So the counts per minute is N, the background counts per minute is NB, so N minus NB. And then you divide that by E, your instrument efficiency, 60. That's just to go from counts per minute to counts per second. If you're working counts per second, you would just ignore the 60. Don't put it in the formula. A would be the area wiped, which is typically 100 centimeters squared, or the active detector area in square centimeters for direct measurements. And if we are doing a wipe, then you would use the factor F, which is the collection factor efficiency. You can either determine this experimentally, although almost no one does. And if you're not, just use a conservative default of 10% or 0.1. Okay, next is the concept of minimum detectable activity, which is spelled out here. The minimum amount of activity in a sample that can be detected with a 5% probability of erroneously detecting radioactivity when none is present, and a 5% probability of not detecting radioactivity when it is present. So basically a 5% chance of having a false positive or a false negative, or another way to say it, it's the level of activity at which you're 95% sure, that it is the activity you're measuring is truly from the radioactivity and is at the correct level. So the formula for the minimum detectable activity expressed in becquerels per centimeter squared is up on the screen, but it can be expressed in becquerels, it can be expressed in becquerels per cubic meter for air, it can be expressed in becquerels per gram, depends what you're working with. But generally, what we mostly see with DNSR licensees would be surface contamination, so becquerels per centimeter squared. So it's the same nomenclature here in this formula as the slide above. So NB would be your background counts. And then E, A, and F are the same: efficiency, surface area, and collection factor. And again, for direct measurements, there's no F, there's no collection factor. And A would be the surface area of the detector. So I've circled T here for time because it's quite important, and some people, might get confused as to what time they should use for different types of instruments. So for a digital instrument that has a scalar function, so I have a picture here of a Thermo Rad-I B20, and it happens to be set up there to count for 300 seconds. So if you have this type of digital instrument where you can just manually put in the amount of time that you want to count for, that's your time, right? That's the amount of time that you've counted for. It's integrating over all of those seconds, and then it spits out an average CPM value at the end. For rate meters, so meters that don't have integrated time counting or scalar counting functions, the integration time is typically only 2 to 7 seconds before it resets and starts integrating again to refresh basically the needle, the meter face. But you can try to consult the manual to see what the integration time is. But if it's not published anywhere, 4 or 5 seconds is probably a reasonable thing to assume for the integration time for a typical rate meter. There are newer rate meters, like digital ones, that may use variable counting, okay? So that means they actually change the amount of time it's integrating for. At lower count rates, they would increase the time, and at higher count rates, they would decrease the time. So again, you should try to look at the manual to see what an appropriate time would be. And other rate meters actually have switches. So they have a slow mode or a fast mode for slower, longer integration times, again, for a rate meter. And the quintessential example here is the Ludlam Model 14C, which I know a lot of you have. It has a fast and slow setting with a little rabbit and a little turtle. So if you look at the manual, actually, the fast mode integrates for 4 seconds the slow mode for 22 seconds. So that would be the amount of time you would plug into the formula. And of course, if you're using it in slow mode, you really do have to hover over the surface for 22 seconds. Okay, then we have uncertainty. Okay, so there's the formula for uncertainty. So we're showing first the standard deviation. So standard deviation for counting radioactivity is basically it's the square root of the sum of the background counts and the sample counts. But if you wanted to express that in counts per second, like we see at the top of the screen here, you can divide by the amount of time, which we've done here. And then if you want to express it in becquerels per centimeter squared, you would also factor in, again, efficiency, the active surface area of the detector or the swiped area, and if it is a swipe, the collection factor. So the bottom formula is what we have published in, again, RegDoc 2.7.1. So, and it's 2 times the standard deviation for the 95% confidence interval. Okay, so it factors in background counts, counts of your sample, time, right, efficiency, and the area and the collection factor. How do I know if the MDA is low enough? Again, published in RegDoc 2.7.1. So there's a couple of different formulas here. One is very simple. It's just saying, okay, I'm going to set the MDA at half of the regulatory criterion for the contamination limit. So that's what the first one is there. And then the other one is making the assumption that a typical measurement is near the applicable, sorry, a typical measurement near the applicable criterion is twice the background measurements. So N is equal to 2NB, and that the counting time T is identical for both. So basically you have the MDA formula plus the 2 times standard deviation would be smaller or equal to the contamination limit. If you do the math on that, you get the formula there that looks similar to the MDA, but the 4.66 is now an 8.12. So both formulas are fine to kind of just establish whether your MDA is low enough, because you definitely don't want your MDA at the contamination limit or the regulatory criterion. You want it below. Okay, so we're not actually going to, plug these formulas in or practice using them. Here I'm saying don't reinvent the wheel. DNSR has sent out this decommissioning tool that I've created. You can use it to do all of these calculations for you. You can take the sheet that's labeled data user defined. You can copy and paste it anywhere, and then you can use it for routine contamination measurements, but you can also use it as an MDA and uncertainty calculator. And if anyone ever has any questions on how to use it, they can contact me. Okay, so now we'll get to the crux of it. We're going to talk about 4 different methods to establish detection efficiency, as outlined above. And again, they're kind of in order of preference, although the first 3 are pretty even. The last one is less preferable. We'll tackle it last. So the first one would be getting a NIST traceable planar source. So there's just a picture I found of what one might look like. Common sizes for these planar sources are 10 by 10 centimeters, so 100 square centimeters, but also smaller disc size ones that are roughly the size of a pancake detector, so about 15 square centimeters. You can also find, they're called planar sources because they have a very, very thin layer, right, above the radioactive material, which will allow electrons, betas, alphas to escape. So when you're using these, you want to make sure, for example, if your source is bigger than your detector, so if you buy a 100 square centimeter source and your detector is a pancake, like 15.5 square centimeters, you want to find the activity under your detector, right? So you would take the reference activity of the source and you would multiply it by the ratio of the 2 surface areas, the surface area of your detector and the surface area of your source, to find the activity under the detector. Again, you want to make sure that you use a repeatable source to detector distance, about 1 centimeter, okay? Use a jig. We recommend using a jig so it's repeatable. There's the formula for efficiency once again, so you calculate efficiency. And then you would want to repeat, document, and update if the result is outside plus or minus 20%, of the initial efficiency determination. You would want to do this annually for every contamination meter used to quantify surface contamination against regulatory criteria. So some people may use their contamination meters as a simple yes, no, like is it above twice background or below twice background, and never use it to relay it to a regulatory criterion for surface contamination. In that case, you don't have to do this. You just have to make sure that it's functionally tested to make sure that the detector is working. So there's a big note here in red. This method cannot be used for short-lived medical isotopes due to unavailability of NIST traceable sources. So this is, of course, unfortunate, but true. Manufacturers are not going to create these NIST traceable sources with very short-lived nuclides. So you're not going to find one of these for technetium-99m. We have to do something else for that. Oops, all right. Okay. So method number 2 is a NIST traceable surrogate source, a planar source, instead of the actual source where the calibration source is the same as the target nuclide. So here it may be because we don't have a choice. We're working with something short-lived. So we have 2 examples here. We have iodine 131 and technetium 99m, 2 commonly used short-lived nuclides. So iodine 131, you can see, has a beta endpoint energy of 606 keV with a branching ratio or probability of emission of 89%, and a gamma energy. There's more than just this one, but the main one is at 364 keV with a branching ratio of 81%. So here what we're trying to do is we're trying to find a surrogate nuclide that has energies that closely, or as closely as possible, match that of the target nuclide. You do the best you can. So examples for iodine 131, you can use chlorine 36 for the beta counting. So chlorine 36 has a 708 keV beta with 100% branch, but we'll deal with the branching ratios after. We can correct for that. We don't really have to worry so much about it. And then barium 133 is the typical surrogate if you're doing gamma counting for iodine 131. It has a quite close gamma line, so 356 keV versus the 364. Branching ratio is different, but again, you can correct for that easily. Technetium 99m has some low energy electron emissions. So there's a couple at 120 and 138 keV. The total branching ratio for those two is about 11%. And then there's, of course, everyone knows, the 141 keV gamma ray line. This is used for nuclear medicine imaging, and it's got a branching ratio of 89%. So a good surrogate for technetium 99m is cobalt 57, used as a surrogate. So it actually kind of works for both. It has electrons at 115 and 129 keV with 3.2% branching ratio, and a gamma at 122 keV with an 85% branching ratio. The issue with using cobalt 57, if you wanted to use it for the electrons, is that it might be hard to find a cobalt 57 a planar source that actually allows the electrons to escape. Usually they're sold as gamma sources. But we'll get into what else you can do for that soon. Okay, so why is it important to try to match energy when you're trying to find a surrogate? So this is what happens when you have different beta energies for different nuclides. So we have an example here. So we're trying to measure, say, F18 and carbon-14. And we're using a typical pancake, a typical thin window GM. So I'll just refer to it as a pancake. So the cutoff energy is roughly 75 keV. That is to say that if betas are above 75 keV, they will get into the pancake detector. And if they're below 75 keV, they will not make it into the detector. And you can see here we have the simulated beta spectrum. So every time there's an emission, there's a beta particle that lies somewhere in this spectrum. But then over time, this is what you get. So for F18, the endpoint energy is much higher. It's 634 keV. And for carbon-14, it's low. It's 156 keV. And when you draw the 75 keV line, it's quite obvious to see that with F18, there's a much larger proportion of the beta particles that are making it into the detector, as opposed to the carbon-14, where there's a bigger proportion of the beta particles that are actually not breaching the window and making it into the detector. So a general statement we can make is that as the beta energy increases, the detection efficiency increases. So these are general statements. I'm sure we can find exceptions, but these are for detectors sensitive to betas. For gamma counting efficiency versus energy, is a couple of plots here, courtesy of Ludlum. Some of you may recognize these. So on the one hand, we have, on the left-hand side, we have a 44.9, which is a pancake contamination meter. And we can see that at very low energies, the detection efficiency actually goes up a little bit as the energy goes up. But then past about 80 keV or so, the efficiency just goes off a cliff. So it's much, much lower as the energy increases. This is normalized to cesium-137 in both cases. And then the other detector is a 1 by 1 inch sodium iodide scintillator. And in this case, you can clearly see that at low energies, so americium-241, cobalt-57, the efficiency is high. And then as the gamma energy increases, the likelihood of having interactions in the detector goes down, so the efficiency goes down. And there's quite large differences in efficiency at different energies. So we can have another generalized statement. As the gamma energy increases, it's the opposite, efficiency decreases. Again, a general statement, there are exceptions. Okay. So still working with surrogate sources, what do we do with the branching ratios? Okay, so what we should do is we should make corrections for the branching ratios of the target versus the surrogate calibration source. They should be applied when the alpha, beta, gamma emissions from the surrogate can be isolated, so separated out. And how do we do this? So we could do it just by the nature of the detector. So for example, a thick sodium iodide detector will only be sensitive to gamma rays. It will not interact with or count betas or alphas. Another example would be a Ludlum 4393, one of these dual detectors, so they can discriminate between alpha counting and beta gamma counting. It's important again to highlight though that pancakes do not discriminate, so they just count, whatever's coming in, alpha, beta, gamma, with varying degrees of efficiency. Okay, another way to separate out the different types of emissions would be with the sources. So we can use separate surrogates for one target nuclide. So an example here would be a cobalt-57 surrogate source that is a gamma source, so designed to block the electron emissions, and then a separate carbon-14 beta source. And both of these sources would be used as surrogates for technetium-99m. So the cobalt-57 would be for the gamma counting, and then carbon-14 would be for the electron counting. There's an example to follow. And then we could also take matters into our own hands and do a bit of shielding for a source. So what we could do here, for example, we could get a cobalt-60 planar source, which is designed to allow the betas and the gammas to escape. And we can use an appropriate thickness of plastic or plexiglass to basically block the beta emissions, establish the gamma counting, and then by subtracting one from the other, then you can also establish the beta counting. And then you can apply that as a surrogate for zinc-65 as an example. So we'll show that. And if you're looking for what thickness to use for a piece of plexiglass, for example, for the given energies of the betas for cobalt-60, for example, here's a shameless plug. You can use the CNSC's radionuclide information booklet that's published on our website that I worked very hard on. Okay, so we're going to show two examples of using surrogates. So one would be this technetium-99m. In both cases, we're going to use it with a pancake. So this is measuring technetium-99m with a pancake. Remember, we're always doing the same steps as method one, right? Which is to say, consider size of the source versus the detector, make sure the repeatable distance, etc. So we have Tech99M. We have the energies. We have 120 and 138 keV electrons with an 11% branching ratio, and the gamma is at 141 keV with the 89% branching ratio. So the cobalt-57 will be used as a surrogate for the gamma counting because the 122 keV matches up nicely with the 141. And then for the beta counting, so in this case, the cobalt-57 source that we purchased, which is actually likely to be the case, is designed to actually block the electron emissions, and only the gammas will get out. And so for the electron counting, we'll use a carbon-14 source because it has an energy that's relatively close, but the branching ratio is very different, but we're going to correct for that. So here are some results, and these results actually should kind of closely reflect what you get in real life. So for cobalt-57, we measured 0.21% efficiency. That would be the gamma counting efficiency with cobalt-57. So then all we have to do then is take that 0.21% result with the cobalt-57 and multiply it by the ratio of the branching ratios, which is 89 for the technetium and 85 for the cobalt, almost the same, but you get up to 0.22%. So this is what you would get for gamma counting efficiency for the pancake for technetium-99m. For the carbon-14, we measured 5.3%. Again, the 5.3% would be multiplied by the ratio of the branching ratios, so 11% over 100%, and we're down to 0.58% efficiency for electron counting of technetium-99m with a pancake. You take the two efficiencies and add them together, 0.22, 0.58, and you get 0.8%. So this is an example. Another example, same idea. Here we're using zinc-65, okay, which would be, I think, maybe impossible to find, a traceable source for this. So we have to find a surrogate for zinc-65. So zinc-65 has a 330 keV beta and a 1116 keV gamma ray. Again, the branching ratios are in brackets. Cobalt-60 is a pretty darn good surrogate. Cobalt-60 has two gammas that are near, right, the gamma line of zinc-65 at 1173 and 1332. And it also has a good beta. It has a beta at 318 keV, which is awfully close to the 330 keV, and you can certainly buy cobalt-60 planar sources. But now what you'd want to do is try to isolate the beta counting from the source. So here again, you can use an appropriately thick sheet of plexiglass. So you'd block the betas, you would count the gammas, and then you would establish the beta counting by simply taking your unshielded count rate from the source minus your gamma CPM, and that will give you your beta CPM. We go down to the results. Again, these are simulated results, but they're probably not too far off reality. The cobalt-60 gamma measurement was 0.39%. Again, you take your 0.39 and you have to multiply by the branching ratios, so 51 over 200. You're left with 0.1%. And then the cobalt-60 beta counting, we got 16.5%. Again, multiplied by the branching ratios, 1.4 over 100, and you're left with 0.23% efficiency for the beta counting. Add the two together, and you have an extrapolated efficiency for zinc-65 of 0.33% for the pancake. Okay, method number 3 would be making your own source. So again, always follow the same step as in method 1, but now you're making your own source. So if you're going to make your own source, you absolutely need a way of establishing the activity of the source that you're making. So here, I've decided to use the example of a dose calibrator because I know a lot of people listening would be nuclear medicine licensees and they have access to dose calibrators. But dose calibrators are only accurate at, at higher activities, so say megabecquerel range, but we're actually trying to make a source in the hundreds of becquerels to a kilobecquerel range. So you can start off with some known amount of radioactivity of technetium-99m as established by your dose calibrator. And then you can do one of two things. You can just wait and just calculate, what the new activity would be after if you waited, say, 48 hours. So I'm showing an example here. One megabecquerel of technetium-99m would be down to 3.94 kilobecquerels after the 48 hours. And then you would extract a known fraction, so a known volume of that activity. You would pipette it out and evenly spread it over a 15 square centimeter wipe. And then you would measure the count rate and establish the efficiency that way with your detector. Or if you don't want to wait, you can dilute down with known volumes. It might take multiple steps. You might have to do a lot of dilution, but you have to add known volumes of water to achieve something that it's in the becquerel per microliter range. And then extract, again, a known activity, something between, this is not an exact thing, but something in the range of 100 to 1,000 becquerels spread evenly over the wipe, and then measure the count rate and establish the efficiency. So this is just one example. If you're lucky enough to have access to a lab, you can do this. I did this myself many years ago at our lab. I got some technetium from the Ottawa Hospital, like an exemption quantity, diluted it, spread some drops on several wipes, and then we have a high purity germanium detector that is efficiency calibrated for the wipe geometry at 10 centimeters. So we established the known activity of the technetium wipes that way. And I measured the efficiency of a couple of different pancake detectors. And we did it on 2 different occasions, and I got between 0.4 and 0.8%. Okay, so again, in method 3, so now you've made your own source, but of course you've made a source that decays away quickly. So you can either repeat this entire exercise annually, right? Or as soon as you've made the source and measured the efficiency, you can transfer the information immediately to a long-lived check source. And then moving forward, use that check source. So of course I used cesium-137 as an example because it seems to be the most ubiquitous check source around. And you'd want to do this for every detector. So once, we're going to take an example, once you've established a detection efficiency of 0.67%, say for detector 1 for technetium-99m with the homemade source, okay, you would then immediately measure the count rate from a cesium-137 check source that you own. And again, you want to make sure that same reference distance is used over and over, year after year. And then you get an efficiency of 0.16% for that detector 1, for example. And then you would just use that efficiency ratio, 0.67 over 0.16, which is equal to 4.2, and you would transfer the technetium-99m information to the cesium-137 check source. So then the following year, detector 1 will be verified and documented with the cesium-137 check source by multiplying the measured efficiency by 4.2, and then you would have your answer. But again, you have to be careful, the same distance. And also with these cheap cesium sources, you have to make sure that they're use the same orientation each time. A lot of them, they'll have thinner plastic on one side, thin enough to let some of the betas out on one side, but too thick on the other side, and they block the betas. So you have to be consistent, and what you should do is actually use the side where you get the higher count rate if you're getting some of the betas out, but always make sure you use the same side of the source year after year, same distance from the source, and decay correct the source. Sorry about that. Okay, and then the last method would be contact your licensing specialist, or you can email me directly for a reasonable and conservative efficiency to use for the target nuclide, or verify the efficiency suggested or published by the manufacturer for the target nuclide. So example, again, technetium-99m. If you look at Ludlam's website for a 44.9, they would say less than 1%. They're not committing to an exact number. We would suggest using 0.5% as a reasonable number to use for technetium-99m. And then what you would do is you would use the same process that I just mentioned, except now you're given an activity, and then you're transferring that information to some long-lived source that you have. So no matter what method that you use, you need to have access to a source of some kind or another, okay? And again, you would transfer the efficiency to a long-lived check source for every detector and verify, document annually, and you would only update the efficiency if the value is outside plus or minus 20% of the initial value. You can, of course, update it even if it's less than that, but we wouldn't expect you to unless the efficiency is falling outside of the plus or minus 20%. And of course, you're free to to verify efficiency far more often than annually as well. I know some licensees do, and that's good, but as a minimum, it has to be done annually. And then just a few notes on method 4. It's definitely the least accurate, so please adopt methods 1, 2, or 3 if possible, if you can. The transfer check sources, so those long-lived transfer check sources, should ideally have the same emission types. It's a should, they may not, but if you can. So as the target nuclide. If the instrument you're determining efficiency for has dual detector channels, like that Ludlam 4393 or a Thermo AB100 as an example, that can discriminate the alphas and the beta gamma channels, you definitely want to use transfer check sources that have those 2 different emission types to verify and transfer the efficiency to both channels if you're using both channels. And be careful, some manufacturers overstate their efficiencies. I've seen this firsthand. For example, Berthold for their LB124 Sint publishes an efficiency for technetium-99m of 7.9%, but it's been experimentally verified at something more like 1 to 2%. So if there's ever any questions, don't hesitate to contact us and ask. Okay. that is the end of the presentation.